Hello everyone, today I'm very glad to present our work. In memory key value store, we call it IMKVS for short. Such as Redis, KDB, and Memcached, they store data in memory so that they achieve ultra-fast speed of processing query. Due to this advantage, IMKVS is very widely used in many online services, such as social network. Also, because all data is stored in memory, IMKVS need to persist data to support backup and disaster recovery. Popular IMKVS use the system called fork to take the snapshot to persist data. This figure shows how to use fork to take the snapshot. First, the storage engine calls fork to create a child process. The child process holds the same data as the parent process. Then, the child process writes data to the hard drive, while the parent process continues to handle queries. We find that there lies latency spike problems while using fork to take the snapshot, as shown in these figures. The figures show in C99 latency and max latency of Redis. With different sizes of instance during normal operation and snapshot, we find that the latency of query grows sharply during snapshot, especially when the instance size gets larger. For example, in a 64 GB instance, the max latency grows from about 6 milliseconds to about 1,200 milliseconds. The cause of latency spikes is that during fork, the storage engine is blocked and out of service for queries. For example, the query arriving at T0 in this figure will be suspended until the parent process finishes the fork operation. As a result, the query will get the response at T1. However, according to our measurement, the execution time of fork is long, especially when instance size is large, as shown in this right figure. We also analyze the reason. We find that the parent process takes more than 97% of execution time in fork to copy the page table to the child process. Moreover, large instance has a large page table with more page table entries to be copied. There have been some work about speeding up fork. The first is transparent huge page. This method automatically promotes 4 KB regular page to 2 MB huge page by operating system. With huge page, the number of PTEs of a process decreases. But this method is not suitable to solve our problem because huge page usually degrades the performance of databases. So many databases recommend disabling this method. Another method is shared page table. This method makes PTEs shared between the parent process and child process so that PTEs do not require to be copied during fork, but they will be copied in a copy-on-write manner after fork. However, this method is also not suitable because we find that shared page table can cause data leakage. The child process can access invalid data and generate an inconsistent snapshot. That is our solution, ACF. The basic idea of ACF is to offload the work of copying the page table from the parent process to the child process, as shown in this figure. With such a design, we can make the fork faster and avoid bringing negative impact to IMKVS. Because this design can keep using regular page and let the parent and child process have private page table. But it is not easy to achieve this design because the parent process may modify a PTE before the child process copies this PTE. For example, at T0, the parent process calls ACF to take a snapshot of this time. At T2, the parent process inserts a new key value pair, K2V2. So the PTE2 of the parent process is modified, while the child process has not copied the PTE2 from the parent process. As a result, the child process will process the pair K2V2 in the future. It is not correct because this pair does not exist at T0. To solve this problem, we detect all possible PTE modifications and let the parent process proactively copies the PTE before it is modified. However, detecting the PTE modification is not easy because PTEs can be modified in many ways by user and operating system. So we fully analyze the Linux kernel to capture all possible PTE modifications. Besides, there may be errors when the child process is copying PTEs, for example, out of memory. When the errors happen, we roll back the parent process. Next, I will introduce how ACF works. Before the introduction, let's take a look at the page table. In Linux, the page table is organized as a multi-level tree. There are generally 4 levels: PGD, PUD, PMD, and PTE. In ACF, firstly, we let the parent process copy PGD and PUD entries to the child process. After that, child process copies PMD entries and the PTE from the parent process. If parent process is about to modify a PTE, it copies a PMD and all PTEs located on the same PTE table to the child process. Because both parent and child process will copy PMD and PTE, we use a flag to identify whether the entries have been copied or not. In order to eliminate the unnecessary copy, next, I will introduce how to detect PTE modifications. We fully analyze the Linux kernel and find out which operations may modify the PTE. We summarize our findings in this table. As we can see, some modifications are caused by user, and some other modifications are caused by the operating system. To detect PTE modifications, we also find out which functions really modify the PTEs. We insert a hook in those functions to detect the PTE modifications. Next, I will introduce the implementation of ACF. We modify some functions on the path to fork and the Linux memory management system, as shown in this figure. We add fork into those functions, while the fork is realized in a module. We also provide the parameter to enable or disable ACF. With such an implementation, we can maintain ACF online without rebooting the system. Besides, the user is free to choose Linux fork or ACF without modifying their applications. Next, I will show the evaluation of ACF. We first evaluate ACF in a local machine with write-intensive workload. We compare ACF with the latest shared page table-based fork, ODF. Although ODF has the data leakage problem, we use it for comparison purposes. Here are the results of P99 latency and the max latency during the snapshot. We use different instances sizes of Redis and KDB. As we can see, ACF outperforms ODF in all cases. We also analyze why ACF performs better than ODF. In fact, both ACF and ODF will cause interruptions in the parent process. This is because in ACF, the parent process needs to proactively copy the to be modified PTEs to the child process, and in ODF, the parent process needs to copy PTEs in a copy on write manner to the child process. When the parent process does the copy, it is interrupted and out of service. The interruptions may happen many times. So we record the frequency of interruptions when using ACF or ODF. As shown in these figures, we can see the parent process suffers from fewer interruptions with ACF. This is why ACF outperforms ODF. We also evaluate ACF used in workloads with different read ratios. With different read-write ratios and different access patterns, uniform random, and Gaussian distribution. Here are the results. We can see ACF can reduce the latency in all cases compared with ODF. What's more, we can find ACF works better for workloads with more SET queries and the uniform random access patterns. We conclude that the larger the modified memory is, the better ACF performs. The ACF is deployed in Redis. In our public cloud, we run two Redis instances with different sizes from the cloud. Compared with using Linux fork, using ACF can really reduce the latency of Redis during the snapshot. In conclusion, in this work, we find that the performance of Linux fork is poor in the process with large memory footprint, which causes latency spikes in IMKVS snapshot. We address the problem from the OS kernel without modifying IMKVS. We analyze the reason why fork performs poorly. We find that the parent process takes very long time to copy the page table to the child process in fork. Based on the findings, we propose ACF, which offloads the most time-consuming part in fork from the parent process to the child process. That's all. Thanks for listening.